Hello Year 11. This is a little video to help you do revision for paper 2. So whether this is you're looking at it just before our PPE in March or you're having a recheck of it during your revision for actual exams coming up very soon, hopefully this will be useful. Okay, now if you want to follow along the exam questions, there's a link at the top of the page here, or you can go to this QR code and it'll bring you to a website that can show you what the exam questions are as well as the mark scheme. Okay, now before we do anything else, I just wanted to remind you, Year 11, that you are in the wonderful position that you are going to get all of the equations given for you. Okay? If this is in future years and you're revising for a test after 2023, okay, you need to learn all of these equations. Okay? But luckily, 2023 year, you get given these. So take advantage of the equation sheet, have it next to you during the exam. Every time you see the word calculation, be ready to find the right equation. Okay? Now, the way this video is going to work, we're going to have different colours on the screen. When it's red, I want you to be listening, I want you to be reading what's on the screen, I want you to be finding mistakes. When the screen is green, that's when you're reflecting, you're writing, and you're fixing mistakes. Okay? Most of the time, you're going to be listening to me and you're going to be looking and seeing where did the student go wrong? How are you going to do better when you answer the question? Okay, I want you to really reflect on how you could improve their answers. Some of the answers are going to be correct, some are going to be half right, some are going to be wrong. Try and find those mistakes. Okay, so first question. This is about a ripple tank. This is one of the required practicals for waves that will be in paper 2. So we've got the diagram of the setup here, where we've got this water inside this ripple tank, we've got a support, we've got this wooden bar and elastic bands, we've got this light source, and it casts a shadow along the ground. Okay, and these little supports, these will wobble up and down, up and down, up and down, up and down, and it will make this ripple pattern. Okay, and the experiment is looking normally at how to find the speed of these ripples, and we do that by investigating the wavelength and the frequency. Now the question says, describe how the student can measure the frequency and wavelength of the waves. You should refer to any equipment the student needs in your answer. And we've got this answer. To find the speed the wave travels at, the pupil should measure the wavelength with a ruler and the frequency of the wave and times them together. Then we've got this next question where we've got this table of results. We've got 1, 2, 3 readings. We've got this frequency, we've got 12.8, 12.4, 12.3, and an x of the mean. And we need to calculate x. And they've done 12.8 plus 12.4 plus 12.3 divided by 3 to get 29.3. Okay, so for the first time, you need to pause the video here and you try and fix any mistakes you can find. Okay, so pause the video now. Okay, moving on. So this wasn't a great answer. Okay, it wasn't really a great answer at all. It's not clear how they would accurately measure those waves, the wavelength of the wave, and it's not clear how they would get the frequency at all. Okay, the best thing at the answer was the idea of using the ruler. Whenever you are looking at required practicals, think, what do I need to measure and what equipment am I using to measure it? And always put those things together. Okay, so if you're going to be measuring a distance, using a ruler, using a tape measure, using a meter ruler, something that you use, a piece of equipment. If you're going to be measuring frequency, we're going to need to use a stop clock somehow to measure the time. Okay, the second question was really going to be frustrating for the student because they've got the right idea. To find the mean, you do add the numbers together and divide by 3. What they've done is they've not used their calculator properly. They've not used brackets. They've not used BIDMAS or BODMAS. Okay, and it immediately should be obvious that it's wrong because 29.3 is bigger than the biggest of the other values. It's bigger than 12.8. Okay, so you need to make sure the answers make sense. So if you want to have a good answer, here's an example of one. So we've got, place a ruler at the side of the screen perpendicular to the wavefronts, take a photo of the shadow, use the ruler to measure the distance between two waves. Okay, much clearer, much easier to follow how we would find that difference between the wavefront and the next. To find the frequency, we would count the number of waves passing a given point, time how long it takes for the waves to pass that point using a stop clock. The frequency is the number of waves divided by time. Okay. The next bit, we're adding brackets. The brackets will give us the correct answer of 12.5. And moving on. Next question. We've got, why was it a good idea to repeat readings and calculate a mean? And we've ticked to reduce the effect of systematic errors. We've got the student change the frequency of the waves in the ripple tank to 20 Hertz, calculate the period of the wave, and we're given this correct equation, period equals 1 divided by frequency, and we've got this calculation here. And at a frequency of 20 Hertz, the wavelength of the waves is 0.012 meters. Calculate the wave speed. We need to use this equation, wave speed equals frequency times by wavelength. Okay, so I want you to find the mistakes, I want you to try and fix them. Pause the video here. Okay, moving on. Now, it is a good idea to repeat readings and calculate a mean, but it's because it's to reduce the effect of random errors. Okay, calculating a mean reduces the effect of random errors. Also allows you to remove anomalous results. It doesn't reduce the effect of systematic errors. Each of your repeated readings would have that systematic error. The same would also have that zero error. Okay, you cannot remove systematic or zero errors by repeating. Okay, this calculation, this is fine. We've substituted the number in, got the correct answer, we've written it down. Perfect. E, this, again, the student has done the correct workings, so they're getting marks for their workings, which is why you should always write your workings down clearly, but they haven't input it into the calculator properly. They've got 2.4, when the answer should be a good deal smaller. They forgot to put an extra 0 in after the decimal point and before the 1 in their calculator. Okay, so the proper answers will be to reduce the effect of random errors. Again, we've got this 0.05 seconds, and here we've got the correct wave speed of 0.24 meters per second. This time we've used our calculator properly. Okay, right, moving on. More stuff about waves. We've got a slinky. It's used to model a sound wave. Okay, and we've got this hand, and it's connected to the slinky, and we've got these different bands along the slinky bits, and we've got these different arrows, and we've got these 5 words that we need to choose to label this figure with. Amplitude, refraction, compression, wavelength, frequency, and then we need to say what type of wave is a sound wave. Tick one box, and we've ticked electromagnetic. Okay, so I want you to pause the video here and fix the mistakes. Okay, moving on. So, this student forgot to label one of the diagram bits. Okay, it's 3 marks, we should use 3 words. Okay, this first bit is not the amplitude, excuse me, this bit's not the amplitude, this bit is a refraction, and this bit is the compression. It's not an electromagnetic wave, it is a longitudinal wave. Okay, so we should have wavelength, refraction, and compression. Okay, you need to know what each of these words mean. You need to know their definitions, and if you know those definitions, these are 4 incredibly quick marks to do. It does not take long to write down 3 words and do 1 tick. Okay, but it's worth 4 marks. Okay, and if you know those definitions, you can get those marks really quickly to allow you longer, okay, to spend longer on those more challenging marks, the harder marks, the ones that take extra effort and extra brain power. Okay, you can spend more time on those, okay, if you're able to quickly answer this accurately. Okay, next question. Figure 2 shows 2 students measuring the speed of sound in air. We've got a wall, we've got 2 students, one with a stopwatch, one with 2 bricks, and the student bangs the 2 bricks together. The sound wave is produced, is reflected from the wall and travels back to the students. So it comes off the bricks, travels along, hits the wall and bounces back. And the answer is, hit the 2 bricks together to make a sound, time how long it will take for the sound wave to travel to the wall and back, divide how far away the wall is by how long it took the sound wave to travel back to find the speed of the sound wave, the words along the sentence. Okay, how can you improve it? How many marks do you think it gets? What would you do to make it better? Okay, so pause the video here, find and fix the mistakes. Okay, moving on. Not the greatest of answers. Okay, it'll get probably 1 mark. It might get 2, but I think that's unlikely. It's certainly a level 1 response answer. Okay, the method would not necessarily lead to a valid outcome. Some of the relevant steps are identified, but the link is not made clear. Timing how long it will take for the sound to travel to the wall and back is important. To make it better, you could put using a stopwatch. That would get a better chance of getting 2 marks. But at the moment, not the greatest, not the clearest of answers. Okay, so here's an example of what you could write to get all 4 marks. Okay, we could measure the distance between the student and the wall with a tape measure. Measure the time taken from banging the bricks together to hearing the echo. Okay, so we hit the bricks, the sound wave travels to the wall and back. In the next bit, double the measured distance to give the distance travelled by the wave. okay, because remember the wave is travelling to the wall and back. Okay, so it goes double the distance between the students and the wall. Okay, the speed is calculated by dividing distance by time. Repeat the readings to find an average. Okay, this answer would definitely be a level 2 response. The method would lead to the production of a valid outcome, and they're identified in a logical sequence. Okay, this would get 4 marks. Okay, next question. We've got a diagram of a wave that we need to label with these either amplitude or wavelength. Okay, now again, this is a place where you could quickly get these 2 marks. If you're really sure about what wavelength is, if you're really sure about what amplitude is, you should be able to quickly identify these marks. Okay, so have a pause, think, are these 2 tick boxes correct? And also, what does amplitude mean? What does wavelength mean? What's an oscillation? What's equilibrium? What's frequency? What are these different words meaning? What are their definitions? Okay, so pause the video here and give it a go. Okay, moving on. So this one, both answers are correct. P, okay, is the amplitude of this wave. From the equilibrium position, where it's not disturbed, to the very maximum, the maximum displacement, the very top of the peak. You could have had from the equilibrium to the trough, but that's not one of the options. Okay, so P is the amplitude. For the wavelength, it is R. From one peak to the next adjacent peak, okay, is one complete cycle of the wave. Okay, we normally will get students to remember the wavelength and draw it like R, because it can be more tricky if we do it across the equilibrium line. Okay, so lots of students would label Q or T as that amplitude, the wavelength, sorry. Now, what does amplitude mean? It's the distance from the maximum displacement of a wave to its equilibrium position. Wavelength, the distance from one peak to the next. Oscillation is the regular variation of position at about a point. Okay, it's a bit of a funny definition that. It's a fancy word for vibration. Okay, equilibrium is the rest position of wave, and frequency is how many waves pass a point in a second. Okay, right, moving on. We have a setup showing how waves can be produced in a string. Okay, we've got a movable bridge, we've got the string, we've got the pulley, we've got masses, we've got this vibration generator, and we've got a signal generator that controls it. Okay, and we've got this method. So the students switch on the signal generator and vibration generator, so the string vibrates up and down, like we've got in this little animation here. Move the wooden bridge until a clear wave pattern is formed between the wooden bridge and the vibration generator, like you can see on that picture. Okay, so the thick line is where the string is at one little bit in time, and the dotted line is where it is in a second or two. Okay, it's difficult for the setup to show it if time is kind of stopped. Okay, it's easier if you can show that animation, but because it's a piece of paper, you can't actually show the animation. We use a meter ruler to measure the length of the string between the wooden bridge and the vibration generator. We record the frequency of the wave from the signal generator, record the number of loops in the wave pattern. The wave pattern is shown in figure 2, so that's that wave pattern, and it has one loop. Change the frequency of the signal generator until a new wave pattern is formed. Repeat steps 4, 2, 6. Give one control variable of the demonstration. Now, there's lots of control variables here, but the most important one is the number of masses. The number of masses is the thing that's pulling the string, it's providing the tension. The tension in the string is what controls the speed of that wave. Okay, the higher this tension, the quicker the speed of the wave that travels. Okay, now, the extra question I would like you to improve and fix is this. The length of the string between the vibration generator and the wooden bridge was about 1.5 meters. The teacher used a meter rule to measure the length of the string. So just 2 reasons why making an accurate measurement was difficult. So, the meter ruler was shorter than the string, and the string is up high from the table, so it would be difficult to measure. I want you to try and figure out, is that a good answer? How many marks do you think they get? What would you write to get all the marks? Okay, so pause the video here and give it a go. Okay, moving on. We've got definitely the first answer, that would get a mark. Okay, if the meter ruler is shorter than the actual distance of 1.5, which it is, it's going to be very difficult to measure it accurately. You'd have to move the meter ruler along, it would be a difficult measurement. Okay, the second part, this might be enough to get a mark, but it's not quite clear enough. So the string is high up from the table, so it'll be difficult to measure. So it is a little bit raised from the table, but I think it's much clearer that if the string is moving, it's going to be difficult to make a measurement. Okay, when the string is moving, it's going to be harder to measure. Okay, I think that's a much clearer answer. Okay, so continuing with this setup, we've got a different set of frequencies. We've got frequency 10, 20, 30, 40 and 50 hertz, and we're showing the pattern that happens between the wooden bridge and that vibration generator. We're also recording the number of loops in the pattern. So the first one's got 1, then we've got 2, then we've got 3, then we've got 4, then we've got 5, and their wavelengths. Okay, now it's important to note, and it comes up in this question F as well, that if you have 2 loops, that's 1 complete wave. Okay, or if you have 1 loop, that's half a wave. So each loop counts for half of a wavelength. Okay, so E says give 1 conclusion about the frequency and the wavelength in the data above. The wavelength decreases. Each loop of the wave pattern is the length of half a wavelength. Determine the wavelength x in the table below, and we've got 0.75 divided by 2 equals 0.375. And then we've got calculate the period of the wave, and the frequency is 30 hertz. Give your answer to 2 significant figures. Use the figure 6 equation sheet. Now, period equals 1 divided by frequency. That's not one of the mistakes. That is on the equation sheet. Okay? And then we're writing the numbers down. 1 divided by 30 equals 0.03333333, and it keeps on going. And then we write down 0.03 seconds for our 2 significant figure answer. Okay? So I want you to find the mistakes. I want you to try and fix them. Pause the video here. Okay, moving on. So, this one, while that's true, the wavelength is going down, we need to have a conclusion about both frequency and wavelength, how they're linked. So this isn't enough to get a mark. This one, all we're doing is dividing the previous number by 2, which doesn't really do anything. It's not the right answer at all. Here, this one is frustrating because they've got the right idea, and what's wonderful is, because they're writing the workings clearly, they're getting 2 marks even if the answer is wrong. If they hadn't written any of these workings, they would have got 0 instead of the 2 out of 3. Okay, so this one, the only thing they haven't done is put it to 2 significant figures properly. Okay, this is a single significant figure. So, to get the answers properly, the wavelength is inversely proportional to the frequency. As the frequency is increasing, the wavelength is decreasing. Okay, to show that it's truly inversely proportional, if we were to times frequency by wavelength, we would get a constant. Okay, the constant would be 30. Okay, 10 times 3 is 30, 20 times 1.5 is 30, 30 times 1 is 30, 40 times 0.75 is 30, 50 times something will also be 30. Okay, now, the next answer is 1.5 divided by 5. So this is the length of the string, which is the 1.5 meters, divided by how many loops there are. Okay, that will get me the length of 1 loop, so 0.3 meters. Okay, so if the one loop is 0.3, I need to times it by 2, because it's half, to get the actual wavelength of 0.6 meters. Okay, this question, we've just changed this answer into 2 significant figures properly. So we've got 0.03 first significant figure and 3 second significant figure. Okay, there will be at least one occasion on your physics exam where this comes up. 2 significant figures or maybe 3 significant figures. Don't lose that easy mark. Learn how to write down the right numbers of significant figures. It's important. Okay? Right. Moving on. Okay, this question is about a rugby player. Okay? We've got a rugby player who's getting tackled by another rugby player, and the question starts with velocity and acceleration of both vector quantities. What is a vector quantity? And a vector quantity is something that has both magnitude and direction. You need to know both vectors and scalars. You need to have a lot of them at your fingertips ready to get quick marks. Okay, and the following ones as a vector is displacement. Distance, time, and work are all scalars, which only have a magnitude. They only have a size. Okay, so moving on to the bits of the question that I want you to try. We've got this velocity time graph. Okay, so we've got time in seconds and velocity in meters per second. And we've got these 3 distinct sections from 0 to 1.6, 1.6 to 3.4, and 3.4 to 3.6. And the first part says determine the acceleration of the player between 0 and 1.6. We've got describe the motion of the player between 3.4 and 3.6. And the answer is the player is stopped as the line is horizontal. This is wrong. I'm telling you, this one is definitely wrong. And it's a really common mistake here. This student is mixing up velocity time graphs and distance time graphs. Okay, so what I would like you to do, I would like you to find and fix the mistakes here and think about what is the motion doing at each of the 3 different steps. Okay, so pause the video here and try and fix those mistakes. Okay, moving on. So, this calculation is actually perfect. It's fine. We've got acceleration is change in velocity divided by time taken. And the change in velocity, we can use the graph to do that. Between 0 and 1.6, we go all the way up to 4 meters per second. So our change of velocity is 4, and the time taken is 1.6. 4 divided by 1.6, 2.5. Okay? Perfect calculation question. This one, the player is stopped as the line is horizontal. A horizontal line in a velocity time graph means constant velocity. It's not stopped. Okay, and in this case, they've misread the question. They're looking at this flat section here, not the section they're supposed to be. Okay, it's a really common mistake. So the first section between 0 and 1.5, it's accelerating. Then it's at a constant velocity. Then it's decelerating. Okay, so to get the marks, we need to write something like this. There is a constant deceleration. Now, if it was a 2-mark question, you might want to include a two-way stop because it goes back all the way to 0. Okay. Right, moving on. Next question. We've got, write down the equation that links acceleration, mass, and force. And we've got mass times acceleration. We've got the player accelerates 25 meters per second squared when the resultant force is 1,800 newtons. Acts on her. Calculate the mass of the player. We've got F equals ma, A divided by F equals m, 25 divided by 1,800 to get 0.01388 kilograms. And it says there's a tracking device that sends data to the computer during the game. What's one advantage of the data being sent during that game? Okay, so I want you to find the mistake and I want you to fix the mistake. Pause the video here. Okay, moving on. So, no marks awarded for this question. Okay, so first, a rugby player with a mass of 0.0138 kilograms. What? 13 grams as a person? Obviously wrong. Okay, they don't get the first answer right, because this isn't it's not an equation. Mass times acceleration does equal force, but you need to put the equals part. If you don't put the equals part, it's not an equation, you don't get the answer. Lots of these questions are coming up in the next exam. You have to use the equation sheet. Copy the equation from the equation sheet into the answer block. If it's got 3 things in the question, you need to have 3 things written down here. If it's got 4 things, you need to have 4 things written down here. Okay? It's not good enough not to include the equal sign and the resultant force. The next bit, the student rearranged first. And if you rearrange first and get it wrong, you get nothing. So you should always substitute first. And it's true that you don't have to wait to the end of the game to get the data, but what's the point? Why is that a good thing? Okay, so it's not really giving you an advantage. Okay, so to get the right answer, to get the right marks, we've got force equals mass times acceleration. So we're actually writing out the full equation. We write the equation, we substitute into the equation, we rearrange, we get the answer of 72 kilograms. Okay, that's where we get our 3 marks. Okay, and one good advantage would be for performance. Okay, you can measure the performance during the actual game. Okay, right, so we've come to the questions that I have done, fixed and corrected. If you want to continue, you can go to this website or go to this QR code and you'll be great with this website. If you're on a phone, you'll have a tick and a cross at the bottom of the page, or something like that. The tick is certainly the answers. You can jot down the answers on pieces of paper and see how good you are, see if you're getting the right answers. Okay, the first 4 questions are the ones that we've done together. 5 and 6 are the ones I'd like you to try and do independently. Okay, right, fantastic work, Year 11, well done. I shall see you all very soon. Bye-bye.